Hey folks, welcome to this episode on orbital hybridization, and this one specifically on sigma bonds. So when we looked at Vesper showed us the shape of molecules, but it didn't explain how covalent bonds were formed, and it also didn't incorporate any kind of quantum concepts. So our new theory is called the valence bond theory, and this theory proposes that a covalent bond forms when there's an overlap of two half-filled valence orbitals. And that means half-filled being one electron with an upspin, one electron with a downspin. Now, the covalent bond is just basically a volume of space between the two atomic nuclei where there's a high probability of finding these electrons that are involved in the bond. So when these orbitals overlap, aka these wave functions, remember that these are all just wave functions, they join together to create a new wave function, and the electrons become spin paired. So here's an example of of a covalent bond between two hydrogen atoms. One of them is an upspin, the other one is a downspin over here. And when they come together, you can see that their spins are going to be paired. Now when they have a head-on interaction, so in this case, if we had a hydrogen and they interacted in a head-on manner where they kind of overlap this way, the electrons are going to be found in this region over here, and this bond that's going to be created is called a sigma bond. So there's actually two types of covalent bonds. There's a sigma bond, and there's also called a pi bond. Now the sigma bond is our strongest covalent bond. The pi bond really comes in when we have multiple bonds, double and triple bonds. And again, in this area is where the electrons are going to be concentrated. So that's why sometimes we can see this kind of cylindrical covalent bond that we signify with a line. Now, when we look at methane, there's a problem here because when we look at our orbital diagram for carbon, carbon actually has 4 valence electrons. So you can see them over here, 1, 2, 3, 4. However, for carbon to make 4 bonds, we actually need 4 unpaired electrons. So in its ground state, being the state that it's naturally found in, it only has these 2 unpaired electrons. So technically, it can only form 2 bonds. The problem is that we know that it's capable of forming 4 bonds, as we see in methane, CH4. So there's a problem here. What's going on? One of the proposed solutions is that we actually promote one of these electrons from the s orbital into one of the p orbitals, and in this case we would call it an excited state. However, what we would see is we'd see a formation like this. Now we do have our 4 unpaired electrons, but the problem is that in this case, carbon would actually form 2 different types of bonds. They would form 3 bonds with these 2 p orbitals, which are a little bit higher energy, and then they would also form 1 bond with this s orbital, which is of lower energy. But studies have shown that in methane, for example, carbon actually forms 4 identical bonds. So this wouldn't be 4 identical bonds. This would be 3 of one bond and 1 of the other. So there's got to be something else. And this is where the topic of hybridization comes in. So Linus Pauling, the same person that gave you electronegativity, proposed that these pure s and p orbitals, so remember like the s orbital, the p orbital, these are considered our pure ones, are actually reconfigured and hybridized into something called hybrid orbitals. So if you can imagine what a hybrid is, it's a combination of maybe 2 or more things, and it's kind of a reconstitution of it. So in this case, what we've actually done is, yes, we've promoted that electron into that p orbital, but what's happened is that when this electron has been promoted, these orbitals actually reconfigure themselves into a hybrid between the s orbital and the p orbital to forming something called the sp3 orbital. So these new hybrid orbitals, they're interesting because they form the same number of orbitals. What that means is that we have 1, 2, 3, 4. And here we have 4 orbitals as well. So we're not creating any new orbitals, we're just reconfiguring the ones that we have. So remember, that means that we can't hold more or less electrons, we can hold the same amount of electrons as we did before. The difference is that they all have the same amount of energy. As you can see, they're not on different steps, they're all on the same steps, and they're also going to have the same shape. Now that shape is going to be kind of reflective of both the s orbital and the p orbital in this sp3 orbital. Now the other thing is that you can see here we have a level of the p, a level of the s. Our sp3 orbital will have an energy that's kind of in between these. So again, a hybrid energy of this. So how do we get this sp3 hybridization? Well, again, in the case of carbon, we had 1 s and we used 3 p orbitals. And so when we actually add them all together and we hybridize them, we create 4 sp3 orbitals. And you can see that they're that these orbitals have a little bit of a different shape than the p orbitals, and they certainly have a different shape than the s orbital. And that's because, again, they hybridize and they share characteristics of both. So when we look at this sp3 orbital, we actually know that because we've used one s orbital for three p orbitals, the sp3 orbital will be 25% character of s and 75% character of the p orbital. So that's why these look more like the p orbitals than they do the s orbitals. Now, how do we get this notation sp3? Well, again, we used one s orbital and we used three p orbitals. Okay, and so if we look at that, we can drop the 1, we get an sp3. Okay, now we are going to be talking about how these superscripts equal an easier way of counting this in a few moments. But just know that it's a hybridization over here between our SPs. We get these sp3. Now, what's interesting is that the way that they arrange themselves, you can start seeing that they arrange themselves in different corners, and when they come together, they create this tetrahedral shape as we've seen in Vesper. We looked at the methane molecule before, and you know that in tetrahedral, you're going to have 4 electron domains, and sure you have there, and they're going to be separated actually by 109.5 degrees, assuming all these atoms are going to be the same. And so anything that has a tetrahedral electron pair geometry or molecular geometry will be sp3 hybridized. So when it comes back to methane, what we know is that here we have our sp3 hybridized orbitals in terms of our carbon. So now carbon has 4 unpaired electrons, all of the same energy, exactly the same. And then we have our 4 hydrogen atoms over here. So again, when these two come together, you'll see that here we have an electron here, an electron here, and they're going to join up to have their spin pair and create our methane. Now again, you can see that this interaction between hydrogen and carbon is in the same line, or it's head-on as we call it. So all of these are going to be sigma bonds that are going to be formed over here. And again, as you can see in terms of our shape, you can see that we're going to have a tetrahedral shape between all this because we're going to have our sp3 hybridized orbitals. So what about something called sp2? So if we look at boron, for example, this would be the ground state configuration for boron. We have 2 in the at 1s, 2 in the 2s, and then 1 in the 2p, so it has three valence electrons. So when we look at boron, boron actually can form 3 bond, which means that it needs to have 3 unpaired electrons. So once again, we can promote this electron into this vacant p orbital, and then what we would have is we'd have a hybrid between the 2s and the 2p, but we'd only use 3 of those orbitals. So that's why we get our sp2. We use 1 s orbital and we use 2 p orbitals, so we get sp2. Now we also do have a vacant p orbital, which is going to be found in the structure of a bond, for example, like Bf3 boron trifluoride. And we'll show you an example of that a little bit later. So when it comes to these hybrid orbitals, the character of the sp2 is going to be 33% s character and 66% p character. And I'll show you why that's important a little bit later. So here's an example. Here we have our 1s orbital, and we have our 2p orbitals that we're going to use to hybridize. And so again, we're going to have this kind of shape. Remember that the sp2 orbitals is going to be 66% p shape or p character. So again, they're going to look more like these p's than they look of these s's. Now what you can see is when you configure them, and if you remember those kind of balloon diagrams that I showed you in the Vesper, you can see that they separate themselves in 120 degree bond angles. So between these over here and these over here, these are going to be 120 degrees. Now when we do this, it actually creates a trigonal planar geometry. So again, anything that has an sp2 hybridization will form a trigonal planar, and they will have about 120 degrees, assuming that all the atoms that are bonded to it, for example here, here, will all be the same. And now we go into sp hybridization, so hopefully you're getting the idea here. Here, if we consider something like beryllium, beryllium has 2 valence electrons, so we always assume that it's going to make 2 bonds. But if we look at it, and the way that it's paired, it's going to be paired up as a pair of electrons in the 2s orbital. For it to create 2 bonds, we need 2 unpaired electrons, so again, we need to promote one of these electrons here. These 2 orbitals hybridize, leaving these 2 orbitals vacant. And so in this case, we've only used 1s and 1p orbital, so s1, p1, we're going to have an sp orbital. And that, again, leaves two p orbitals vacant. So in this case, our character is going to be a little bit interesting because we have 50% s and 50% p in terms of the character of the hybrid orbitals. So again, in this case here we have, so this is not really depicting the way that it should be. You're going to have more of an S character than a P character, but you can see that they hybridize again in these kind of newer shapes, something that looks something a little bit between these two. And when they actually bond together, you're going to see that the maximum space apart between these two orbitals is going to be 180 degrees, which is going to become linear. So the problem is when we look at nitrogen and phosphorus. Phosphorus and nitrogen are in the same group. They both have 5 valence electrons, and they both have a outer configuration of 2 electrons in the s orbital and 3 electrons in the p orbital. Now this electronic or this orbital diagram is of nitrogen, so you can see that it has the 2s and the 3 in the p. So we know that nitrogen, if we look at the Lewis structure of nitrogen, we have 1, 2, 3, 4, 5. Nitrogen has a lone pair of electrons, and it has 3 unpaired electrons where it can form bonds with. So the only way that we can actually do this is actually we promote one of these electrons over here, and again we hybridize these orbitals into sp3. Now it looks a little bit different than what we saw in carbon, but remember it's still going to be sp3 because we're using one s orbital and 3 p orbitals to create our new hybrid orbitals. So these new orbitals will be sp3, but you'll notice something very interesting over here is that by promoting one of these electrons, we've actually created a lone pair. Where does that lone pair see? Well, there's our lone pair in nitrogen. So now, nitrogen can actually go ahead and create these 3 unpaired electrons, which can create 3 bonds. Now, phosphorus can do the same when it forms PCl3, but the problem is, how do we explain PCl5? So when we get into PCl5, remember that phosphorus is actually in the 3rd period. And when n is equal to 3, L is going to be equal to 0, 1, and 2, which means that you have s orbitals, p orbitals, and you have d orbitals available to you. So phosphorus actually makes use of this. It uses that d orbital and actually promotes electrons into that d orbital. So in this case, it'll take this electron and promote it in here. So now what you're going to be looking at is you're going to look at a hybrid between an s orbital, 3 p orbitals, and 1 d orbital. So when we look at that, you're going to have 1 s, you're going to have 3 p's, and you're going to have 1 d orbital. So what we're going to call this is we're going to call it sp3d hybridization. Now, obviously, if you can see this, we're not using all the d orbitals, so we're actually going to have 4 of these orbitals left vacant as 3d orbitals. And so here's the kind of orbital filling diagram that you would see here. So you can see that our s, our p's, and our d's hybridized, and you have 5 lone electrons, so 5 unpaired electrons, all of which can actually now form a bond with chlorine. Now, if you think about chlorine and its valence shell, it's going to have 1 unpaired electron in its last orbital. So in this case, that 1 unpaired electron can have a head-on interaction with this and will form a bond, and you'll have Cl here. And that will happen with all of these different ones over here. So this is the geometric shape that it's going to take. It's going to be a trigonal bipyramidal. You can see that here if we connect 1, 2, 3, here we create a kind of a trigonal pyramid, and then we have 2 of these. Okay, so now we have trigonal bipyramidal. So again, when we look at this, the angles in the equator are going to be 120 degrees, and the angles between the equator and the axis are going to be 90 degrees. So you'll have both angles in this geometry. So when we look at hybridization, there must be a little bit of an easier way, and sure there is. We can actually just count the number of electron domains around the central atom. Now, when it comes to counting this, lone pairs and bonds are all considered electron domains, and it doesn't really matter if you have a single, double, or triple bond, they're all considered as one domain. So if we look at, for example, just a Lewis structure of CH4, we already know what the answer is for what the central atom, again being carbon. We can count the number of electron domains around carbon. Well, it has 1 electron domain there, 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 and there. So it actually has 4 electron domains. So this means that it's going to have 4 orbitals used. Now, how can we figure that out? Well, going back to what we were saying before, if we look at the superscripts, that can help us figure out which hybridization is. So we know that we have to use S. S has to be used based on the Aufbau rule. So if I need to figure out what superscript I need to add to make it equal to 4. So if I have 1s, I'm going to need 3p to get into 4. How does that work? Well, 1 plus 3 gives me 4. So that I know my carbon is going to be sp3 hybridized. Okay, and that's how it works. If we look at beryllium, for example, beryllium would form 2 bonds, for example, BEH. It only has 2 electron domains. It doesn't have any lone pairs. So you're going to have 1 electron domain, a second electron domain. So again, if I know I need to have S1, I only need P1 over here to equal to 2. So I'm going to be sp hybridized for beryllium. So here are some examples. We already saw that with the BEH2. So here we have our interaction. Now in here, remember that this is going to be, you're going to have some hybrid orbitals of Be, and then there's going to be an interaction. So you can actually kind of see that. Here's a kind of a hybrid orbital of there, and then the H is overlapping over here. So that would be our sigma bond over there. So we actually create 2 sigma bonds, one over here and one over here. And again, this is sp because it only has 2 electron domains. We look at something like BF3. Again, BF3 doesn't have any lone pairs, but you can see it has 1, 2, 3 hybrid orbitals. So that must equal sp1, s1, p2. So it would be sp2. Okay, so again, I used 1 s orbital, 2 p orbitals, so that would be 3 electron domains, which I see right over here. And you can see fluorine has a head-on bond over here, so in this area right over here, and over here, they're going to be sharing electrons, and these are all going to be examples of sigma bonds. So you can see from the side as well, remember that boron had that vacant p orbital, and so that vacant p orbital actually has this kind of configuration that goes above and below the actual trigonal planar geometry of this BF3. And finally, we go into something called ethane. Ethane over here will have a carbon and a carbon, and they're all going to be single bonded. There's no lone pairs. So all of these, if you look at this, it has 1, 2, 3, 4 electron domains. That means it's going to be sp3 hybridized. Same thing with this carbon, 1, 2, 3, and 4. So sp3 hybridized. And you can see that they're overlapped over here. This will create that sigma bond here. But also don't forget that there's going to be sigma bonds between every interaction between carbon and hydrogen. So we're going to have all these different sigma bonds in this case here. So here's just a summary of all the orbital hybridizations, the geometries that they'll take, and the bond angles. One thing that we didn't talk about is when we get into 6 electron domains, you're going to have this hybridization of sp3d2. And we were talking about character before. Character actually has a relationship to the bond strength. Now, the more the hybrid orbital has an S character, so the higher percentage of S character, the stronger the bond is going to be. Now, you have to remember, when you look at these S orbitals lie very, very close to the nucleus. Okay, so they'll be in this area of probability around the nucleus. So the closer these electrons, or the higher the percentage of an S character orbital, the closer these electrons will actually be to the nucleus. And the closer that are going to be to the nucleus, the shorter the bonds are going to be. And because they're shorter, there's going to be more stability, and therefore you're going to have a stronger bond. So when we look at something like an sp3 hybrid versus an sp hybrid, well, remember that you only have basically 2 orbitals here that are hybridizing, and so you're going to have a 50-50% character. So these orbitals will create a stronger sigma bond than sp3 hybrids, again, because you're going to have less of that S character. The electrons are going to be found farther away from the nucleus, so there's going to be less stability and a weaker bond. So thanks very much for watching. Stay tuned. We're going to have another hybridization episode, this time talking about our multiple bonds, aka our pi bonds. See you soon.